Good morning and welcome. My name is Rafal of Wrobel. I'm representing here Newcastle University, and this is presentation on heat pipes in thermal management of electrical machines, theoretical feasibility study. Let's start with a short introduction into subject. The concept of heat pipes in thermal management of electrical machines is not new and has been investigated over several decades with different intensity, and early examples developed in 70s. The initial work was focused on induction machines and showed up to 20% improvement in power density of electrical machines where heat pipes were used in thermal management, either on the stator winding or rotor side. A typical heat pipe is constructed as a metallic vessel containing working fluid and frequently also a weak structure. This two-phase system relies on phase change from liquid to vapor and from vapor to liquid, which is introduced by the heat on the evaporator side, and then heat removal feature, heat exchanger on the condenser side, and a weak allows for a return of the working fluid, so capillary pumping from condenser to the evaporator. A typical copper water heat pipe is shown here, and this one is the most popular as it offers reasonable performance measures when it comes to heat transfer and also operating temperature range. That phase change mechanism allows for achieving significantly higher equivalent thermal conductivities along heat pipe that could be found for any metallic or ceramic alternative, ranging from 5,000 to 100,000 watts per meter Kelvin. And here, as a comparison, copper is somewhere around 400 watts per meter Kelvin. A typical datasheet of a heat pipe includes heat rate and also some mechanical parameters among other information, including temperature range as an example. For the purpose of this analysis, a permanent magnet traction machine was used with a basic information listed in the table. Two winding arrangements being analyzed. The first one with a good slot utilization and conductor fill factor equal to 50% is the baseline for the analysis. The second one with reduced conductor fill factor is being designed to accommodate for heat pipe base heat removal. Important to note here that both windings or both coils include the same number of turns per coil, and the change in the conductor fill factor has been achieved here by changing the outer diameter of the conductor. The purpose of this analysis is to evaluate potential benefits and also limitations of the of using heat pipes or employing heat pipes in thermal management, with focus on the stator winding assembly, looking into compatibility issues associated with additional loss or thermal heat transfer across multiple sub-assemblies. Two alternative thermal management systems were investigated. As a baseline for that investigation, a typical arrangement when it comes to a stator housing was used. So we have a tooth wound coil on the stator core pack, which is then interfaced with actively cooled housing. The two alternatives here that are heat pipe based systems rely on the heat guide heat pipe heat pipe heat guide sub-assembly, where the pink rod here represents heat pipe and the gray triangular shape represents here the heat guide. So the supplementary system S1 uses both actively cooled housing and then heat pipe heat guide sub-assembly to assist. And the second system, where the heat guide heat pipe plays the primary heat removal role, and then the housing in that case is naturally cooled. Anisotropic properties of the materials and various contact resistances were considered in the analysis. We focus on the contact thermal resistances between the heat guide and winding, and then the heat pipe and heat guide, as this have an important effect on the overall heat transfer from the stator winding assembly. The initial sensitivity analysis assumes DC loss in the winding as a main loss source or heat source. Those two contour plots show heat transfer improvement with baseline winding, baseline heat transfer or thermal management system used as a baseline. S1, again, as a reminder, refers here to supplementary heat removal heat pipe based system, and S2 primary. The thermal conductivity along heat pipe here is relatively low and representative of aluminium rod as a starting point. On the x-axis here we have the heat guide to winding interface, and on the y-axis we have a heat pipe to heat guide interface. This is emulated as an equivalent air gap. In the best case scenario for the system 1, we can achieve 34% improvement with 22 amps per meter square for 180 degrees C winding hotspot temperature. For the system 2, well, the system underperforms here, so the performance is poorer than the conventional water jacket housing called system. Here we have 11% reduced heat transfer and 17 amps per meter square. It is also important to note here that the contact thermal resistances between those two sub-assemblies have a significant impact on the overall heat transfer improvement in both systems. When replacing that aluminium rod with actual heat pipe and changing the thermal conductivity here to 8000 watts per meter Kelvin, a considerable improvement can be found, 41% for system 1 and 22 for system 2 when it comes to heat transfer, and then current density 23 and 20 amps per meter square DC. It is also interesting to note that now the variation of that heat transfer versus two interfaces is less abrupt. Further increasing the thermal conductivity along heat pipe to 30,000 watts per meter Kelvin doesn't lead to significant increase in the overall performance. And here again, we have a 43% improvement in terms of heat transfer and 25 for system 1 and system 2 respectively, and that leads to DC current for 180 degrees C winding hotspot temperature, 24 amps per meter square, 21 amps per meter square. Interestingly is to find what that leads to, how that heat transfer improvement translates into machine output improvement. Here on this slide we have a comparison of the torque improvement for both systems, and for the heat pipe with the highest thermal conductivity, equivalent thermal conductivity analyzed here, and that corresponds to 17% in torque improvement and 24 amps per meter square, and 2% torque improvement and 21 amps per meter square for system 1 and system 2 respectively. It is worth to note here that this is rather optimistic here. We just assume simply a DC winding losses only and a perfect heat guide to winding and heat pipe to heat guide interfaces. Clearly that output will deteriorate as more realistic operating conditions are assumed. In an attempt to do so, we've analyzed additional power losses starting with the additional winding losses at AC operations. So we have a ratio of AC to DC winding losses versus frequency here, showing that baseline machine, although well utilizing the slot, leads to a double of the losses at the AC operation as compared to that alternative winding design with a poorer slot utilization. Another important factor is the additional loss associated with that heat guide heat pipe assembly. A heat guide portion of that assembly is assumed here to be made of ceramic material with high thermal conductivity, which doesn't introduce any additional losses. However, the heat pipe itself, the shell and the wick, they do contribute to the loss figures generated in the stator winding assembly, and here they're represented as a heat pipe loss to a DC winding loss. And for heat pipe operating hot, that is approximately 6% of the DC winding loss. Interestingly, that copper wick structure has a comparable loss to aluminium rod that is shown on the figure. The next slide illustrates the total power loss per single stator winding sector. Here we have all losses accounted for, both winding, AC and DC, core loss and any additional loss associated with the heat pipe assembly. This is represented here as contour plots for 180 degrees C temperature of the winding, the hotspot temperature, versus rotational speed and DC current density, and that's been derived for maximum torque per amp to provide a clearer view on both losses and then heat transfer effects. What is interesting to note here that the baseline machine is capable of sustaining 15 amps per meter square at low speed for that 180 degrees C hotspot winding temperature. As we increasing speed or increasing frequency, the AC losses lead to reduction of that DC current to cope with the additional heat source and additional losses to be then removed from that stator winding assembly. For the same current density, the alternative winding generates less loss, and this is associated with lower volume of conductors. The alternative heat pipe based systems, so S1, so supplementary, and S2 primary, allow in general for higher loss to be removed from that stator winding assembly, but in both cases, as we increasing the operating speed, that initial current density is being reduced significantly. Looking at the individual loss components in more detail, we've generated 2 or 3 additional figures where we have a normalized power loss versus rotational speed. Again, just a simple maximum torque per amp operation is analyzed here with all loss components, including DC winding, AC excitation, AC rotational winding, and then iron losses. In the case of the heat pipe system, also heat pipe loss components. The results been normalized to the to the loss at low speed baseline machine, showing that the system 1 allows for considerable improvements in terms of sustaining that additional loss for that 180 degree C hotspot winding temperature over a wide range of or whole range of speeds. And the situation looks slightly differently for the system 2, which performance is poorer than the baseline one. You might have noticed that those figures are slightly different to those that I've just shown you on the previous slide, and this is because here I've just assumed more realistic operating conditions where there is imperfect contact between heat pipe and heat guide and winding, to make this more realistic and a fairer comparison. That improved heat transfer removal and then capability in terms of sustaining higher loss leads to increased output torque, and this figure illustrates normalized torque versus rotational speed for all analyzed cases. Again, here we're analyzing this more realistic scenario where we have that imperfect contacts, and that results suggest 10 to 30% increase in output torque depending on operating speed. The system 2 here underperforms, but it depends on what is compared here. Perhaps if comparing complete assembly power density, system 2 might be comparable or better than baseline one. And then observation and conclusions. Here we've analyzed off-the-shelf heat pipes and the applications in thermal management of electrical machines. Such a retrofit doesn't necessarily lead to optimal design and then the best possible performance. Consequently, a solution that is tailored to specific application and electrical machine design might offer better performance measures. Another consideration to make here is that compatibility of applying heat pipes in electrical machines is important, especially thermal, mechanical, and electromagnetic aspects that might considerably affect the overall performance measures. And as this analysis was initially aimed to hardware evaluation, but due to COVID-19, I was unable to progress that work. At some point, it would be good to evaluate practically gains and limitations of the heat pipes by experimentation. I hope that you've enjoyed the presentation. If you have any questions, please do contact me. I look forward to hearing from you. Have a nice day. Bye.